consider that you are analyzing a granular material with the size parameter x prime 5 mm and the width parameter n equal 3 of its volume-based RRSB Q3 distribution being known. In order to do this analysis, first discretize this particle distribution into 10 classes. Of course, consider sensible limits for the classes based on the known parameters. Subsequently, you should determine the number of particles in each class. Note that the RRSB parameters correspond to a Q3 distribution. Next, also calculate the delta Q0 values, same as the values of the discrete Q0 distribution. Finally, you should fit the Q0 distribution to obtain its parameters and plot it. Sounds interesting, so let's get started. The solution for task 1 is quite simple, as you see here. 10 classes with a class increment of delta x 1 mm is a suitable solution. Thus, we span from 0 to 10 mm our classes. Note that we use the Q3 values at the upper class limits. This is because cumulative distributions are defined at the upper class boundaries. The next task is a bit more involved. We first calculate the volume of a single particle in each class. Note that we use the average particle diameter xm in this class, which is simply the average of the upper and the lower limit of the class. This volume is denoted with VPI on this slide. Also, we calculate the delta Q3 values. This is done by considering the differences of the Q3 values between individual classes and hence easily done. This is also the key to the next step. We calculate the total volume of the particles in each class, denoted here as delta V class. Note that we have considered a total particle volume of 1 cubic meter for this latter task. However, you will see that the total volume of the particles we consider does not matter for the resulting distribution. Next, we can calculate the number of particles in each class simply by dividing delta V class with a single particle volume. After summing up all the particles in each class, you see this is quite a lot. Since we arrive at almost 200 million particles, we are ready for the final step. We simply divide the number of particles in the class with the total particle count. This gives the delta Q0 values. Now we shift to the next task that is quite straightforward. By accumulating the delta Q values from each class, we find Q0. The fourth and last step is to determine the parameters of the cumulative Q0 distribution. The first important thing to note is, same as for the Q3 distribution, that Q0 is defined at the upper class boundary. See the data in the first column. We could then directly fit the Q0 distribution with the RRSB distribution. However, we prefer to first linearize the RRSB distribution. This shows that we should fit a transformed Q0 value, here denoted as y, and which is equal to the double logarithmic function shown here on the right. The transformed particle size should be the logarithm of the upper class limit x upper, as you see here. The slope of this fit is then equal to n, and the intersect d can be used to calculate x prime. This was a bit fast, So we have summarized all the details of this calculation and the fitting procedure in the accompanying Excel sheet rrsb example.xlsx. Let us finally have a look at how well the fit of Q0 with the RRSB distribution function works. As you can see, it is not perfect but quite okay. Also note that the shape of the cumulative Q0 distribution is qualitatively different compared to the Q3 distribution. This is quite usual since number-based distributions naturally have higher Q values for smaller particles, simply because their number is much bigger than that of larger particles. This was it already for our excursion to particle size distributions. I hope you liked it.